Hi, I'm Aurélien Géron, and today I'm going to explain how synthetic gradients can dramatically speed up training of deep neural networks and even often improve their performance significantly. We will also see how they can help recurrent neural networks learn long-term patterns in your data, and more. Synthetic gradients were introduced in a paper called Decoupled Neural Interfaces using synthetic gradients, published on arXiv in 2016 by Max Jaderberg and other DeepMind researchers. As always, I'll put all the links in the video description below. To explain synthetic gradients, let's start with a super quick refresher on backpropagation. Here's a simple feed-forward neural network that we want to train using backpropagation. Each training iteration has two phases. First, the forward phase, we send the inputs x to the first hidden layer, which computes its outputs h1 using its parameters theta1, and so on up to the output layer. And finally, we compute the loss by comparing the network's outputs and the labels. Then the backward phase. The algorithm first computes delta 3, which are the gradients of the loss with regards to h3. Then these gradients are propagated backwards through the network until we reach the first hidden layer. The final step of backpropagation uses the gradients we have just computed to tweak the parameters in the direction that will reduce the loss. This is the gradient descent step. Okay, that's it for backpropagation. Now, suppose you want to speed up training. You buy 3 GPU cards and you split the neural network in 3 parts, with each part running on a different GPU. This is called model parallelism. Unfortunately, because of how backpropagation works, model parallelism is inefficient. Indeed, to compute the loss, you first need to do a full forward pass sequentially. Each GPU has to wait for the previous GPU to finish working on a training batch before it can start working on it. This is called the forward lock. Notice that the model parameters cannot be updated before the loss is computed, and this is called the update lock. And finally, we cannot update a layer's parameters before the backward pass is complete, at least down to the layer we want to update. This is called the backward lock. The consequence of all these locks is that GPUs will spend most of their time waiting for the other GPUs. As a result, training on 3 GPUs using model parallelism is actually slower than training on a single GPU. So the main idea behind synthetic gradients is to break these locks in order to make model parallelism actually work. Let's see how. First, we send the inputs to the first hidden layer. Then this layer uses its parameters theta1 to compute its outputs. So far, nothing has changed. But now we also send the outputs h1 to a magical little module m1 called a synthetic gradient model. We'll see how it works in a few minutes, but for now, it's just a black box. This model tries to predict what the gradients for the first hidden layer will be. It outputs the synthetic gradients delta 1 hat, which are an approximation of the true gradients delta 1. Using these synthetic gradients, we can immediately perform a gradient descent step to update the parameters theta 1. No need to wait. This hidden layer equipped with its synthetic gradient model is effectively decoupled from the rest of the network. This is called a decoupled neural interface, or DNI. In parallel, the second layer can do the same thing. It uses a second synthetic gradient model M2 to predict what the gradients will be for the second hidden layer. And it performs a gradient descent step. And so on up to the output layer. This time, instead of using a synthetic gradient model, we might as well compute the true gradients directly and use these gradients delta 3 to update the parameters theta 3. And we're done. Notice that we only did a forward pass, no backward pass. So just like that, training could potentially be up to twice faster. So just to be clear, these synthetic gradient models are only used during training. After training, we can use the neural network as usual based on the trained parameters theta 1, 2, and 3. Okay, now let's see how this technique enables model parallelism during training. Once again, let's split the network into 3 parts, each running on a different GPU card. And the CPU will take care of loading the training instances and pushing them into a training queue. We start by loading the first training batch, and while the first GPU is computing h1 and updating its parameters using synthetic gradients, we can already load batch number 2 and push it into the queue. Then, while layer 2 takes care of batch number 1, layer 1 can already take care of batch number 2. No need to wait. And so on, so you get the picture. Now, each layer is working in parallel on a different batch, so all GPUs are active. They are much less blocked, waiting for other GPUs to finish their jobs. And we can continue like this until the end of training. As you can imagine, this can dramatically reduce training time. However, every time we go from one layer to the next, we need to move a lot of data across the GPU cards. This can take a lot of time, and in practice, it can far outweigh the benefits of this architecture. But if you have a deep neural network composed of, say, 30 layers, then you can split it in 3 parts of 10 layers each. You can use synthetic gradient models at every hidden layer or every few hidden layers, or just at the interfaces between the GPU cards. With so many layers, the time required to copy the data across GPU cards is now small compared to the total computation time. So the GPU cards spend much less time waiting for data, and you can hope to train your network close to 3 times faster than using regular backpropagation on a single GPU card. So model parallelism actually works. Great, now it's time to open the black boxes and see how the synthetic gradient models work. Let's focus on a hidden layer I. It has its own synthetic gradient model MI, which produces synthetic gradients delta I hat. And these synthetic gradients can be used to update the hidden layer's parameters without waiting for the true gradients to be computed, as we have just seen. This model can simply be a small neural network, for example, a single linear layer with no activation function, or it could have a hidden layer or two. We will simply train the synthetic gradient model MI so that it gradually learns to correctly predict the true gradients delta I. For this, we can just train the synthetic gradient model normally by minimizing a loss function. We can just use regular backpropagation here, nothing fancy. For example, we can minimize the distance between the synthetic gradients and the true gradients, in other words, the L2 norm of their difference, or we can minimize the square of that distance. But this begs the question, how do we compute the true gradients delta I? If we need to wait for the loss function to be computed and for the true gradients to flow backward through the network, then we have somewhat defeated the purpose of synthetic gradients. Fortunately, there's a neat trick to avoid this. We can just wait for the next layer to compute its synthetic gradients delta I plus 1 hat, and then we just backpropagate these synthetic gradients through layer I plus 1. Okay, this does not really give us the true gradients delta I, but hopefully something pretty close. Of course, if the next layer happens to be the output layer, then we might as well compute the true gradients and backpropagate them. Over time, the synthetic gradient models will get better and better at predicting the true gradients, and this will be useful both for updating the parameters correctly and also for providing accurate gradients to train the synthetic gradient models in lower layers. And that's it. You now know what synthetic gradients are, how they work, and how they can speed up neural network training. But there are a few more important things to mention. Firstly, synthetic gradients can be used pretty much on any type of network, including convolutional neural networks such as this one. Just add synthetic gradient models after some hidden layer, and that's about it. Now, each synthetic gradient model's outputs must have the same shape as their inputs. That is, the same shape as the outputs of the layer they are attached to. So, for example, M1's outputs must have the same shape as the outputs of this convolutional layer. Suppose it's a convolutional layer with 5 feature maps of size 400 by 200, then that's exactly the shape that M1 must output. That's a 5 by 400 by 200 array. In practice, you can use a shallow convolutional neural network that preserves the shape of its inputs. So for example, a couple convolutional layers with 0 padding and stride 1 would do just fine. Here's another important point. Until now, the input of each synthetic gradient model, MI, was only the output of the corresponding layer, HI. But it is perfectly legal to provide additional information to the synthetic gradient model so that it can make better predictions. For example, we can give it the labels of the current batch. This is called a conditional decoupled neural interface, or CDNI. In the paper, the authors show that CDNI consistently performs better than regular DNI, so it should probably be your default choice. So in the paper, they experimented with the MNIST dataset of handwritten digits using various architectures and training methods. In particular, they used this fully connected network with 3 to 6 hidden layers of 256 neurons each. They used batch normalization and the ReLU activation function at each hidden layer. And here's a graph presented in figure 2 in the paper. It shows the learning curves for 3 to 6 hidden layers and for various training methods. For example, when trained using regular backpropagation, the network reaches below 2% error on the test set, and it gets better when you add more layers. Using synthetic gradient models at each hidden layer, the final performance of the 3-layer networks ends up being better than before, but it takes time to train this synthetic model. So overall, it's a little bit longer than backpropagation. When you add more layers, the network's performance actually decreases and training time increases. That's not great. Note that each synthetic gradient model is actually composed of 2 hidden layers of 1024 neurons each, and 1 output layer of 256 neurons. They also used batch normalization and the ReLU activation function in the hidden layers here. Finally, they tried training the network using conditional DNI. The network gets better when you add more layers, and with 6 layers, it actually reaches the best performance overall. Moreover, as you can see, this is the fast learning architecture. It reaches less than 2% in just a few thousand iterations. Surprisingly, they used very simple synthetic gradient models without any hidden layers here. I'm curious to know why they did not use the same synthetic models for DNI and CDNI, because it feels like we're comparing apples and oranges. Anyway, it clearly demonstrates that CDNI performs much better than backpropagation on this task, both in terms of final accuracy and training speed. There are many more results in the paper if you're interested, in particular great results with convolutional neural nets. Another great application of synthetic gradients is in recurrent neural networks. At each time step t, a recurrent layer takes the inputs xt, as well as its own outputs from the previous time step ht-1, and it produces the output ht. It is convenient to represent RNNs by unrolling them through time across the horizontal axis like this. First, the recurrent layer takes the inputs at time t equals 0, and it has no previous outputs. It then outputs ht equals 0, and at the next time step, it takes the inputs xt equals 1 and the previous outputs ht equals 0. To be clear, these 2 boxes represent the same recurrent layer at 2 points in time. Then it outputs ht equals 1, and we could go on and on and on. However, during training, we have to stop at one point, or else we will run out of memory. We can then compute the loss based on the outputs produced so far, and we can perform backpropagation. And finally, we can update the parameters of the recurrent layer. This technique is called truncated backpropagation through time. It works well, but it has its limits. In particular, since we only computed the loss on a few outputs, we know nothing about the future losses. So in practice, this means that the network cannot learn long-term patterns. So let's see how synthetic gradients can help solve this problem. Instead of stopping at time step t equals 3, let's unroll the network for just one additional time step. But instead of using its outputs to compute the loss, we send them to a synthetic gradient model. It estimates the gradients for that time step, delta t equals 4 hat. And we backpropagate these gradients through the layer to get an estimate of delta t equals 3. We can then perform regular backpropagation through time by mixing the true gradients and the estimated future gradients. Finally, once we have all the gradients we need, we can update the parameters of the recurrent layer by performing a gradient descent step. We must not touch the last unrolled cell because this would change its output ht equals 4, and we're going to need it in a minute to train the synthetic gradient model. So by using synthetic gradients in a recurrent neural network like this, we can capture long-term patterns in the data, even if we unroll the network through just a few time steps. Now let's see how we can train the synthetic gradient model. For this, we will need to run the network on the next few time steps. So let's move forward in time. Okay, clean up a bit and push this to the left to have more space. Okay, now we run the RNN on the next few time steps. Okay, we compute the loss. We add an extra time step, and we use the synthetic gradient model to estimate the gradients for that time step. And just like earlier, we backpropagate these synthetic gradients and we mix them with the true gradients. And now this process gives us something pretty close to the true gradients for time step t equals 4. And we can use these gradients to train the synthetic gradient model. Next, we can use the gradients we computed to update the RNN's parameters. And boom. Of course, we could repeat this process many times, and both the RNN and the synthetic gradient model would get better and better. It does add some complexity, but you can bet that the main deep learning libraries will soon hide this complexity from us, hopefully. If you need some motivation, here are some amazing results. This graph is a simplified version of figure 4 in the paper, and it comes from DeepMind's great blog post about synthetic gradients, which I highly encourage you to read. The link is in the video description below. It shows the performance of various RNNs on the Penn Treebank task, which is a language modeling task. The horizontal axis shows training time, and the vertical axis shows the model's error, measured in bits per character, BPC. The 3 dashed lines are the learning curves of a regular RNN using backpropagation through time, unrolled through 8, 20, or 40 time steps. So the more you unroll the RNN, the longer it takes to train, and the more data it requires, but also the better the performance it eventually reaches. Now, compare these 3 dashed lines to the solid line on the left. It shows the learning curve of an RNN trained using backpropagation through time, unrolled through just 8 time steps, but this time using synthetic gradients. As you can see, the model reaches the lowest error, even better than the model unrolled through 40 time steps, and it takes roughly half as much time and data to train. That's really impressive. Okay, next, yet another really interesting idea in the paper aims to break the forward lock. So recall that the forward lock is the fact that we need to wait for the lower layers to finish before we can compute the top layers. It may sound impossible to break this lock, but it's in fact quite simple. You can just equip any layer you want with a synthetic input model. For example, let's add a synthetic input model I3 to layer 3, which is the output layer. It allows us to skip the hidden layers 1 and 2 by computing H2 hat, which is an approximation of H2, the inputs of layer 3. We can just feed H2 hat directly to the output layer, and ta-da, we've just broken the forward lock. As you might guess, once we eventually get the output of the hidden layer 2, we can use it to train the synthetic input model. This is really the exact same idea as earlier, but going forwards rather than backwards. In fact, we can even use the same trick as earlier to go even faster. Instead of letting the signal propagate through the whole network to compute H2, we can just use the synthetic input model from the previous layer and feed it to the hidden layer 2, and this will give us something hopefully close enough to H2 to train I3, the synthetic input model of layer 3. To conclude, let's look at the data flow of a fully decoupled neural interface that uses both synthetic inputs and synthetic gradients. First, the synthetic input model receives the next training batch and computes an approximation of the layer's inputs, hi-1 hat. Then the hidden layer computes its outputs hi and feeds them simultaneously to the next layer and to its own synthetic gradient model. These gradients are backpropagated through the hidden layer, which gives a reasonably good approximation of the true gradients for the previous layer. The gradients delta i-1 are just sent back to the previous layer, which will use them to update its own synthetic gradients model. And immediately after that, we can update the layer's parameters using the synthetic gradients delta I hat. At some point, we will receive the outputs of the previous layer, hi-1, and we will use them to train the synthetic input model. And lastly, we receive the gradients from the next layer, and we use them to train the synthetic gradients model. And that's it. The DNI is ready to handle the next training batch. If you want to learn more about synthetic gradients, I encourage you to read the paper itself, as it touches on a few more topics, such as many implementation details or how synthetic gradients can help 2 recurrent nets communicate efficiently when they don't tick at the same rate, and so on. So check out the links in the video description. There are several interesting blog posts and implementations, and I might add my own implementation at one point. If you want to learn more about deep learning, check out my book, Hands-On Machine Learning with Scikit-learn and TensorFlow. In particular, there's a whole chapter on running TensorFlow across multiple GPUs and servers. There's also a German version and a French version, and I believe a Chinese version should be out in the next few weeks. And that's all I had for today. I hope you enjoyed this video and that you found it useful. If you did, please like, share, comment, subscribe, and you can also follow me on Twitter if you're into that. See you next time, and I wish you a very happy new year.